I'm sure pretty much everyone in the audience is familiar with our next presenter, Professor Stephen Tsai. Professor Tsai began his career in composites at Ford Aerospace before continuing on to Washington University, the Air Force Materials Laboratory, and eventually Stanford University. Over his career, he started the Journal of Composites Materials, was elected to the National Academy of Engineering, and has made numerous discoveries such as the Tsai-Wu failure criterion and Tsai's modulus. His recent work on the subject of double-double laminated composites has the potential to make laminate design simpler and easier to understand while requiring significantly fewer tests to establish design allowables. So everyone please welcome Professor Stephen Tsai.
Thank you very much. It's my pleasure to share with you what we believe is a better laminate theory for the design, testing, and manufacture of composites. In this chart, we show the difference between quad. Quad is a standard practice that is fixed with 4 angles, and then the variables are the number of plies. So in this case, we show a hard laminate, which is 5221. And the problem with this particular laminate theory based on the quad is that it is a function depending on how many plies you have. In this particular case, that it is a symmetric laminate, so there are 10 plies. So if you change from 10 to 9 or 10 to 11, you have to change, for example, 5. 5, you go to 6, or 5, you go to 4, but you cannot go to 4.5 or 5.5. And then you have all the problems that associate with the quad. A much simpler configuration for the laminate would be called the double-double, that the double-double make the angle as a variable. So you have here 75 and 15. And then the advantage of that is you only have 1 ply of each, so that the laminate only has 4 plies as a building block, whereas a quad, you have many more. And of course, the angles are continuous variables, so you can have 75, you can have 76, or whatever you have. So you can interpolate, which you cannot interpolate in the case of quad. So here are the examples of quad of various number of plies. As you can see, the lowest is 8, the highest, in this example, say 32 plies. So they are fixed in 4 angles. And then the problem with that, among all the other things, is that the number of stacking sequences are in the millions. You can see 24 for the simplest, all the way into the millions of stacking sequences. So the design becomes very, very difficult because there are so many variables, and you do not know which one to pick. So in double-double is in the bottom one, that is a match exactly what you have on top. And you can see the simplicity between what is on the top, which for design, testing, and manufacturing, and how much simpler it could be. You have only 4 angles. Not only the 4 angles, there's only 4 plies. And therefore, it's much easier. And you can see what happened on the column here. To the right, and you have the quad, and you have the double-double. The double-double, the most important part is homogenized, so that if it's homogenized, you can taper without fear, whereas in the quad, you have to be symmetric, and then you have the stacking sequence, and you cannot drop plies. You can drop plies to save weight, you change the laminate. And the other thing, that quad is very difficult because the plus 45 and minus 45 are on different levels, so that the D16, D26 in your in the equilibrium equations are not 0, whereas a double-double, you have high enough repeats, they're 0. So they're much simpler. There's a truly orthotropic, and the quad, the Dij is anisotropic. So in case of a quad, the double-double, it's much simpler. You can see that for any given laminate, it is the same for all materials you measured in the trace values. So it's much simpler, and then much solutions. You can have possibly one solution that applies to all materials. And the other thing that makes it simple is the use of trace. Trace is a measurement of the sum of the diagonal term of the stiffness matrix. And these are the carbon epoxy materials. Their value of trace. This is the value of trace. And these are the normalized stiffness matrix in the double-double. So that you have this A11, this is A66, this is engineering constants, this is Poisson's ratios for the entire double-double laminates in increments of 15 degrees. You can see 0, 15, and so forth. And then what is happening is you can see the separation between materials to the left and the lamination. Lamination is purely geometry. So the numbers here is a percentage of trace. So the trace value is 232. This is 89% of that for this particular laminate. So what is happening if you have a ratio between two materials, any materials is based on the trace, then that applies to all laminates. So you don't have to worry about if it's 20%, 20% difference. Conversely, if between two laminates, you can have two laminates at 53%, 50%, say that's 5% difference, and that 5% difference of this between the two laminate applies to all materials. So materials and laminates are much simpler, and they are uncoupled, and so that when you measure properties, you don't need to measure all materials and all laminates. In fact, you only need to measure one material and one laminate, and you can scale all the others. And in the case of failure envelope, it's the same thing. And to the left is the first by failure. We plot all the failure envelopes in strain space. This is all for the degraded, so the last by failures. So it turns out that the first by failure is controlled by all angles depending on the combination of the strain, whereas the last by failure is only the longitudinal tension and compression. So for the last by failure is much easier because you only have two parameters to deal with. And with that, you're able to rank materials in terms of strength. And this is the plot of all the area of the failure envelopes, the area of failure envelopes. And in this case, we use the radius of this circle, and then we normalize by the materials. As you can see, these are the materials for each materials, all the 17 laminates as a normalized value is the same. You can see they're all the same. So that you have the same relationship. This is a material rating. The material rating is here, and you can see it's very, very accurate. There's 2% difference or less. And so if you know the laminate difference, and then you can do the material difference. So we have the same relationship. If the one material is higher 20% than that, that applies to all laminates. And in the other case, we do the laminates. Here's a laminate. Again, you can see they're all flat tops. So if the two laminates is 20%, and that applies to all materials. So everything becomes much easier to do. And there you can come out with a universal curve between a strength versus stiffness, strength versus stiffness. And this is a rating of the stiffness is a rating of the strength. You can plot a universal curve. This for the A11, A22. Of course, you can get the A66. So here, the difference, as I mentioned, in the case of quad, you cannot reduce the thickness because you change the optimum laminate. And therefore, you have a problem with stacking sequence. You have a problem with blending. And it becomes, optimization becomes almost impossible. And whereas a double-double is homogenized, you can save weight by reducing the number of repeats. and the properties does not change. And here's an example of a omega stringer. Here is a 32 ply at the thickest section. This is a 4 ply at the section. So when it's homogenized, you can drop the plies and you can put the ply drops on the exterior, and therefore the interior is perfectly without any discontinuity. Therefore, it's a much better laminate. And then say, how much weight do you save? We have examples of four cases, and these are you save more than 50% of the weight. And then there are different ways you can laminate. The best is to match the precise ply drop every place, but it's much easier you do the ply drop along one axis or two axes. There are two ratios, or you can use a constant thickness, and you can see you give up little weight savings, but you gain much in ability to laminate. And then the rate of lamination, depending on the aspect ratios, is something like six times that of the quad. The quad, you have lamination of 4 angles. Here you do one axis layup, and you only have without cross plying. And in particular, then we propose to use a pre-ply double. Pre-ply example, meaning whether we build in the angle, in this case is 0 plus minus 60. And because when we use thin plies, and the double are a perfect match, and that just shows these are the properties. And then you can have all the advantage. You have less minimum gauge, and you have one axis layup, you're homogenized, it's easy to tapering, and ply drop in singles, and no interior defects. And this is an example of the what we call pre-ply double, and this is the view of the traditional, and this is what we believe is the future, in which case you can suppress failure modes, and this is an example of the 5-to-1 ratio in the ply thickness. This is 5 times thicker than this side. This is fatigue over open hole, and you can see the delamination, edge delamination around the hole around the edges, whereas you don't have that. So that we think that opportunity to go to pre-plied double is what we think is a future of composite laminates. And therefore, composites, double is straightforward, is the same laminate plate theory, and all the data that between quad and matching double, they are either equal or double is a little higher than the quad. And it makes simplified and testing is much easier because you can scale. That shows a difference. And then you can use thin plies and pre-plying, which we have shown, and you have significant savings of weight. You have one axis layup, you can do tapering, and we can learn how to scale. So that solution is a generic solution, so you can scale if you change materials and or laminate. And we believe we can do design level much faster and simpler than what it is. And also many applications we have found that between far beyond aerospace and sporting goods. And here the last slide shows you can download all the books and reports that we have relative to the double. And this is a link, and you can download all of them free. Thank you so much for your attention.
Dr. Tsai, we're going to open it for questions now.
Sure. Thank you.
Dr. Tsai, it's Dave Paddock from NASA Langley. Good to talk to you again. I wanted to ask you if you had what you're lacking for built objects from double that you need to further demonstrate and prove out the numerical theory that you've made here. Do you think you've had enough testing of actual builds, or or what are you needing next? I guess is my question.
Well, that's a great question because people always ask us. We always tell people you got to switch to double because that's where the future is. The reluctance is really two parts. One is a lack of data. We just don't have the data that the quad data has. A quad has 60 years history, and ours is something like 6 years, 5 years. And the thing which I mentioned, every test data we have done, in other words, smooth or open hole or CAI, everything that we have done, and which many of them are published, are show that double are just as strong, if not stronger, in all the tests. But of course, we don't have all the tests with the number that people have with the quad. So that's one thing. We are trying to generate as much as fast as we can and try to fill in that gap. And the other thing is that you need to study. The double is no different from quad. It is the same laminated plate theory. So there's nothing that you need to learn. You can do the buckling, you can do the vibration, and everything you do is simpler. Is simpler in the case of double. But you have to get into it. You listening to presentations like this doesn't do you anything. But you have to go into it, and you have to spend a little time. And we try to make it as easy, as simple as possible. But person who has done it, as you would expect, we talk with students. Students have no problem. They do everything, and they say, "Oh yeah, that's double. It's no big deal. They can do triple or whatever they want." But for the professionals, it doesn't come that easily. So that's where I think is an issue. But we're making very good progress, particularly the last few months. We have some big companies and coming to us. We are working with them and to hopefully improve their products.
Hello, Dr. Tsai. Good to see you. Misha Pollack, Stanford, class of '05. Nice to see you.
Thank you.
You showed in one of your slides, one of the benefits is, that you're not dropping or, losing or adding any plies in the middle of a laminate. Often in fabrication, and especially in HyperX, we give the users the ability to do a study between how they want to do the layup. Do they want to do it interleave? Do they want to do an hourglass? Do they want to do a diamond? Is there any benefit to those different sizes using the double, or do you just always recommend to do it as a pyramid and drop the outside plies as needed?
I'm not familiar with the different ways of dropping plies, but in the case of double, the key is homogenization. Homogenization across the thickness, also across the plane of the structure. And so our recommendation is if you do homogenize the entire structure or in large areas, and then your ply drop becomes very simple. Because you don't have a stacking sequence or blending issue as you do with quad. So in our case, we recommend there's a study on the Airbus wing, and the Airbus wing 350 had over 200 laminates, and then you take the average of all the laminates. It turned out to be a replacement for double is 0 plus or minus 54 degrees, and it changes totally how the process, how you will build it and so forth. So we think that there's a lot we can learn, and to be able to simplify to go to double, then the key is to take advantage of homogenizations, and so that you don't have the stacking sequence problem that was so difficult to solve.
Thank you
I
very
hope
much.
I answered your question. Yeah.
Thank you.
Okay, Dr. Tsai, thank you so very much for your presentation. I believe you've answered all the questions, and we look forward to seeing you again.
Well, thank you so much for having me. Appreciate it.